what a perpendicular bisector is. We have done perpendicular bisectors. We've constructed them, all right? And we're going to do some more construction with them. But it basically cuts a line segment in half, okay? And it cuts it in half at the midpoint, specifically at a right angle, okay? So in a triangle, when you have a perpendicular bisector that's coming from the vertex of the angle of the triangle down, it's going to cut this line in half perfectly, and it's going to meet it at a right angle. That is what a perpendicular bisector does. The perpendicular bisector theorem, which is on page 207 in your books, does say that if a point lies on a perpendicular bisector of a segment, it is equidistant, or meaning the same distance from the endpoints of the segment. So if you have a perpendicular bisector, then every point on this must be the same exact distance from each of these endpoints, which means that C must be the same exact distance from those endpoints, okay? So this says if CD is perpendicular to AB and AD, which is this, is congruent to BD or equal to BD, the lengths, then something else must be true. What must be true is that your line segment AC must be congruent to your line segment CB. If every point on this line is the same distance away, then that means from the endpoints, then that means A is the same distance away from C as B is from C. So if your perpendicular bisector runs through that vertex, you are going to have equal measures there. The converse is also true. If CA is equal to CB, then CD must be perpendicular to AB. That has to be true. And then if that's true, then AD must be congruent to DB. And so you create this equality when you have a perpendicular bisector that runs through the vertex. It has to run through the vertex for that to be true. Has to run through the vertex for that to be true. And we're going to see that perpendicular bisectors don't always run through a vertex. But when they run through a vertex, it creates this triangle, which means it's created with an isosceles triangle, by the way. All right, so an isosceles triangle, you're going to have the base perpendicular bisector always go through the vertex of your isosceles triangle. And that's why these pieces are true. So let's look at finding these values. Look at numbers 1 and 2 there. Numbers 1 and 2 on this same page. Find the value of x. Well, they have told us by marking that this line segment is congruent to that line segment, which means this goes through the midpoint. They've also told us by marking that this is perpendicular because we have a right angle. So we know that this is a perpendicular bisector that runs through the vertex, which we automatically know two things. We know these line segments are congruent. They're noted that way. But we also know that these are congruent. And so if they want us to solve for x and we know that these are congruent, we're just going to set them equal to each other and solve. And so we're going to say that 7x plus 24 equals 13x minus 48. To solve for x, I'm going to move my variables to one side and my numbers to the other. So I'm going to subtract 7x from both sides. All right, it's going to cancel on the left. I'll have 24 over here. On the right, I will have 6x minus 48. I am then going to add my 48 to both sides to move my numbers to the other side. We'll cancel on the right. On the left, I will have 72 equals 6x. My final step is divide by 6. And I know that x equals 12. If they wanted the length of the line segments, I would plug that back in. So if they wanted me to find the length of this segment, I'd plug it back in and solve. But if they just want me to stop at solving for x, then I'm done. So go ahead and do number 2. Solve for x. All right, so angle bisector. Just like a segment bisector cuts a segment in half, an angle bisector cuts an angle in half, all right? And so for this one, we have an angle bisector theorem. If point is on a bisector of an angle, then the point is equidistant from the sides of the angle. And so if I wanted an angle bisector, we've also constructed these. You were to put an arc here, and then you put two arcs out here and connect it. What they're saying is if this line here, AD, is cutting this angle in half, and then we have a perpendicular here from A to B is perpendicular to this line segment, and AC is perpendicular to this line segment. It creates also a special case where those two are congruent, because every single point on this line must be the same distance from these two lines. Every point on your bisector has to be the same distance from your angle sides. All right, your angle sides. And so to create the distance, it has to be perpendicular. Shortest distance between two lines is a perpendicular. Okay, so this is perpendicular. All right. And so if this is a bisector, then that means this has to be the same distance away from the other one. And then the converse is also true. If you know these are perpendicular and that these are congruent, then you must know that this is the bisector. So if you know this is the bisector, then you know it's the same distance. If you know these are the same distance, then you know it's the bisector. All right, so bisectors cut angles in half. And as long as these are perpendiculars here, that's the distance, then you know the distance is the same. You know the distance is the same. All right, so the first one has told us two things. We have these congruent marks on the angle, which tell us this is an angle bisector. And we have the perpendicular marks, which tell us that this is the distance from these points to the sides of the angle that we cut in half. So if this is an angle bisector and these are perpendicular, then that means these are congruent. And so if they're congruent, to solve for that, we're just going to set them equal to each other. 4x plus 30 equals 9x minus 5. And to solve for x, we're going to get our variables to one side, our numbers to the other. Subtract 4x from both sides. It's going to cancel on the left. 30 equals 5x minus 5. Add your 5 to both sides. You're going to get 35 equals 5x. And so to solve it, you get that x equals 7. The same is true for 9. If these are congruent and that is perpendicular, meaning the distance, then we can assume that this is an angle bisector and that these are congruent. So go ahead and solve for x over here. Yes, ma'am. Okay, thanks. Caroline. All right. So I have the perpendicular bisectors that they meet at one point called the circumcenter. Now the circumcenter is always equidistant from the vertices. All right, so it means it's going to be the same distance from each vertex. All right, so if I were to take each vertex and measure it, I would get the same distance, which means that B to P is the same distance as C to P as A to P. Those are all the same distance away. All right? It's not going to be the same distance from each side. It's going to be the same distance from each vertex, okay? So two things about the circumcenter here. It is made up of the perpendicular bisectors, and it is the same distance from every single vertex, all right? So if I were to list the perpendicular bisectors here, if I were to list those, I would say the perpendicular bisectors are going to be from each side to the center there, to the circumcenter. So the perpendicular bisector then of AB is the segment P to D. All right, so that bisector is PD. If I were to look at the bisector of BC, perpendicular bisector of BC is PE. And if I were to look at the perpendicular bisector of AC, that would be PF. So those are my perpendicular bisectors, which make up the circumcenter. Where those meet is the circumcenter. So then the circumcenter is going to be the point P. That is my circumcenter. So then which segments are congruent? Which segments are congruent? Well, those are from my circumcenter, which is the point P, to each vertex. So that means from A to P is going to be congruent to B to P, which is going to be congruent to C to P. Those three are congruent from each vertex to my circumcenter. From each vertex to my circumcenter. So you'll notice then that since it is a perpendicular bisector, then that means that each side has some congruent segments. So AB has congruent segments from A to D, and D to B is also congruent because it is the perpendicular bisector. From B to E and E to C is also congruent because it is the perpendicular bisector of that one. And then from A to F and F to C is also congruent because that was also the perpendicular bisector. All right? It says Z is the circumcenter of this triangle, all right? So they've told us a good bit of information by telling us that particular statement, all right? We know that every single side is congruent to, is in congruent parts, okay? If it's the bisector, it means that T to W and W to V is congruent. It means that T to X and X to U is congruent. It means that U to Y and Y to V is congruent, all right? So they've already told us all of that. We actually also know a little bit more. We know that each of these are also congruent to each other from T to Z, U to Z, and V to Z, because those are the vertices to the orthocenter. Or to the circumcenter, rather. All right? So they want us to solve for these segments here. And so we're going to look at each segment individually and see if we can tell. So they have TU. TU. All right? So let's first talk about where it is. Well, TU is right here. What do I know about TU? Well, I have two congruent parts of TU, and they've given me one of them. From X to U is 19, which means that from T to X is also 19. So what is T to U? 19 plus 19, right? So that's going to be 38, right? So the next one they're asking us about is VY. That's this little piece right here. Well, I know that that's whole piece, V to U, is 34. How does that help me solve from V to Y? Divide by 2. So from V to Y is just going to be 17. So the fact, all they had to do was say it's a circumcenter, and they've given us all this information to solve for. Look at the next one, U to Z. U to Z. All right? So U to Z is from a vertex to the circumcenter. So all I have to do is find another vertex to a circumcenter. Well, they gave me V to Z, and that's 21. V to Z is 21. Well, if V to Z is 21, then U to Z is 21, and T to Z is also 21. And so I know that U to Z is just going to be 21. All right. Now the next one's going to require some calculation. The next one that they're asking for is W to V. All right, W to V. Now, so far, I don't have any information about this side. They didn't give me the total length from T to V. They didn't give me T to W, right? I know the distance from W to Z is 15. I know the distance from V to Z is 21. I also know that because this is a circumcenter, what type of angle is this going to be? It's going to hit it specifically. It's a perpendicular bisector. So what is this angle? Is the right angle, isn't it? So I basically have this triangle here. I know that from W to Z is 15. I know that from V to Z is 21, and I have a right triangle. We have a theorem from Algebra 1 that deals with right triangles. What is that theorem when I know two sides and I need the third side? I have a right triangle, and I know two of the three sides. Almost. What's the theorem that tells me if I know two sides of a right triangle, I can find the third side?
The
Pythagorean theorem. What is the Pythagorean theorem?
A squared plus B squared equals C squared.
Right. So we did this in Algebra 1, and it's coming back to us here. My side lengths A and B are my legs of my right triangle. My hypotenuse is the C. They want me to solve for W to V. So I can use the Pythagorean theorem to do it. I can say that A squared plus B squared, which they gave me, equals C squared. And then I just solve. And you can use your calculators to do it if you need to. I have A squared plus 225. 21 squared is 441. So A squared is going to equal the square root of 216. It doesn't have a perfect root. So if you round it, if you use your calculator, you should get 14.7. 14.7. And you would use a calculator to do that so that you have a rounded amount. 14.7. Right? So Pythagorean theorem will help in these because we know we have perpendiculars. We have right angles. If you have a right triangle, you can use the Pythagorean theorem to solve. All right? The last piece then is pretty straightforward because it is simply the whole length. We just solved for W to V. We said that is 14.7. That is half of the length. So how do we find the whole length? We're just multiplying by 2. So we should get 29.4. 29.4. So go ahead and try. For your incenters, it is the angle bisectors of each angle in your triangle. So the angle bisectors of the angles of the triangle intersect at one point. So if I were to cut each one of these angles in half and draw the line out from there, A to P cuts the angle A in half. B to P cuts the angle B in half. And C to P cuts the angle C in half. And those all intersect at one point, which is called the incenter. All right? Now, the incenter is actually the same distance from all the sides. Just like the circumcenter was the same distance from all the vertices, the incenter is the same distance from all the sides. So while my angles are all cut in half, these lengths here that go from the incenter perpendicular down to the side is the same distance. Now, it does not cut the side in half, okay? So it's not like I'm going to cut that side in half. What it does is it's just the same distance. It's same distance. Now, just like we talked about when we did perpendicular bisectors though, if I have a perpendicular bisector, if I have an angle bisector and these lengths are perpendicular, then that means that these sides must be perpendicular. So while it doesn't cut the side of the triangle in half, those pieces will be the same distance. So those pieces will be equal, which means for angle C, from C to E and C to F will also be equal. And from A to D and A to F will be equal. So it doesn't cut the side in half. So from A to D and D to B are not the same length. It does give you congruent measures in this triangle. From A to D and A to F would be the same. And so for each of these, you do have congruent pieces. Doesn't cut your side in half, but it does give you some congruent pieces. It does cut your angle in half. So that means that this little tiny angle and that tiny angle are congruent for each one of these. It does cut each angle in half. So my angle bisectors then would be from A to P. That's an angle bisector. From B to P, that would be an angle bisector. And from C to P, that would be an angle bisector, which means my incenter is the point P. My incenter is the point P. And then my congruent segments are created from my vertex to each piece here. So A to D and A to F are congruent. B to D and B to E are congruent, and C to E and C to F are congruent. All right? So the same thing happens with the incenter. You do have some perpendiculars because we're talking about the distance. And so if you look at the first one here, it wants us to find some lengths. So let's look at this first one together. It wants us to find from N to P. From N to P. All right. Now, a couple things here. I actually already know some pieces of this. I know based on the definition of my incenter that P is the same distance from every single side. So from P to N is the same distance from P to O, which is the same distance from P to M. Well, P to M is 8. So I already know N to P. I don't have to calculate anything. I already know it's 8. Because I know that my incenter is the same distance from each side, and they gave me one distance to a side, which was 8. So I automatically know that N to P is 8. They're also asking for N to K. into K. All right. Now, into K, based on what we just talked about, should be the same distance as K to O, right? Because this is the angle bisector, and these two pieces are the same. So again, I don't have to do any calculating for this. If I know K to O, I also know K to N, which is going to be 17. And then they want from P to K. P to K. All right. So I just did two pieces of a right triangle. I know that N to P is 8. I know that N to K is 17. They want the hypotenuse here. I'm going to use Pythagorean theorem. 8 squared plus 17 squared equals what they're looking for. When I square these and add them, and then I'm going to take the square root, which is going to be approximately 18.8. All right. So go ahead and try number 5 there.